Okay, we've seen all the standard results of integration, so we're done, right? Well, not quite. So the standard results are really good because they open up a vast variety of functions that we can now integrate that we couldn't integrate before, but they are limited in that they only apply to having the argument x. So we can integrate e to the x, we can't integrate yet e to the 13x minus 10, or we don't even know if that can be integrated. And with differentiation, what we did to get around that was introduce the chain rule. And I want to refresh your memory of how it works because we're going to essentially look at a reverse chain rule for integration that works sometimes. So let's look at these as some examples and we're going to differentiate them and see what we can say. Now there is obviously chain rule shortcuts for each of these. I'm just going to do this long form, this one last time, just to show there's no tricks up my sleeve. So if I wanted to integrate this, you split it up into saying this is u to the power of 5, where u is 4x plus 3. You differentiate them both, and then you multiply those two things together. So our dy dx for that function would be 20 u to the 4, or 20 times 4x plus 3 to the power of 5. I'm actually going to split this up for reasons that will become obvious at some stage. This is going to be 4 lots of 4x plus 3 to the 4. Blimey. Yeah, okay, that's right. What about the second one? Well, we've got e to the u. U is 5x minus 3. Differentiate them both. E to the u stays the same. U just goes to 5. And so our dy dx is equal to 5e to the u, which is 5e to the 5x minus 3. Which I'm going to split apart and say we've got 5 times e to the 5x minus 3. What about the next one? Well, we're saying y is cos u, u is 6x minus 2. Differentiate them both. Cos goes to minus sign, remember. U goes to 6. Multiply them together. And we've got minus 6 sine u, which is minus 6 sine of 6x minus 2. I'm going to split that and say we've got 6 lots of minus sine 6x minus 2. And then the last one we've got here, we've got y equals cot of u, and we just introduced that in the previous slides. And the differential of cot u is minus cosec squared. Don't expect you to learn that just yet because it is one of those that's given to you in the formula book, but just be aware it exists. Dy dx is therefore minus 3 cosec squared u, which is minus 3 cosec squared of 3x plus 8. And again, I'm just going to split that up into 3 times minus cosec squared 3x plus 8. So why have I done it like this? Well, the general idea is that if you've got an argument that looks like ax plus b, so that means a linear expression, then the thing you get when you differentiate it is kind of just like you differentiated it as normal, so multiply by the power and drop the power by 1, also times by a. So this is a times just the differential of something to the power of 5. And the same is true for all of these. If this is our ax plus b, our a is 5, and all we ended up doing was multiplying the differential of e by 5 and sort of keeping the argument the same. All we ended up doing here was multiplying the argument by 6 because it's 6x minus 2. All we did here was multiply the argument by 3 because it's 3x plus 8. And I think in the chain rule we said, yeah, because that's the differential of the bracket. But it's quite useful because, as we saw on the previous slide, constants and coefficients at the front don't really affect integrals. And this means this is a case where we can actually use. Now, the general form of what we've said is this, that if we differentiate f to the ax plus b, then we get a times the differential of that function of ax plus b. So how are we going to use this? So how do we deal with this? Well, the first thing I'm going to do is I'm going to divide the function that I've got with y by a. So obviously this is true. And so this statement, so divide by a would just give me 1. This statement must also be true. All we've done is like multiplied them both by 1 over a, and multiplying by constants does not change anything to do with the actual differentiation. We can take that out as a factor. So if the first statement is true, then the second statement is true, and then we can make this third statement by integrating the whole thing. So if this differentiates to there, then this must integrate to here. So the integral of our f dash of ax plus b must be 1 over a times f of ax plus b. Now if you didn't follow any of that proof, that's fine. You just need to be able to use this rule. But this is essentially the start of our reverse chain rule. Let's see how we'd use it. So these are some very similar functions to what we just worked with. I had to change one of them because it wasn't a standard integral that we could use. How do we apply this? So going from the left, first thing we do is we'd look at our 4x plus 3 to the 5, and we'd say, okay, well, we want to integrate something that looks like f dash of ax plus b. This is to the power of 5, and normally if we integrated something to the power of 5, it would go up to the power of 6, and we divide it by 6. But also, we need to apply this 1 over a to our result. So our a is equal to 4 in this case, so our integral of y is equal to 1 over 4 times our integral of 4 of a bracket to the 5. We could simplify that a little bit. We could say we've got 4x plus 3 to the 6 all over 24, and I guess we should really have a plus c on there. Okay, what about the second one? Integral of y. So e doesn't change. So still that's our f of ax plus b. And then we divide by a. And there's not really much we can do to simplify that. Let's just stick the plus c on. What about our third one? Well, cos integrates up to sine. So that's our f of ax plus b. And then we divide by a plus c. What about our last one? Sec squared, that integrates up to tan. So we've got tan of 3x plus 8. And then we apply our 1 over a. So I probably have explained that in like a fairly convoluted way. But all it boils down to is that if you've got this nice linear function inside something that you know how to integrate, so we know how to integrate cos, then all we need to do is integrate cos, keep that function the same, and then apply this 1 over a situation. So we integrate sec squared, leave this the same, and 1 over a. Okay, let's see if we can do it in a bit more complicated questions then. So let's apply this rule to some definite integrals. This means we're going to have to put limits into our functions as well. That's fine. So here, on the first one, we've got a case of 2 different functions. So we might want to consider them separately, but we can probably do it all as one. So the first one we've got is 1 over 7x plus 3. And we're thinking, well, that looks like 1 over x. And we know that goes to ln. So the reverse chain rule version of this would be to say that that was going to go to ln of 7x plus 3 with our 1 over a at the front. What about the second one? We've got e to the 5x minus 4. Well, we know e doesn't change, so that's still going to be e to the 5x minus 4 times our 1 over a, or divided by a. Definite integral, so no plus c required, and then we just need to sub in our limits, which I'm going to do while paused. So if we sub in 3 and we sub in 2, we get this lovely looking expression, which we're not going to be able to simplify much, but let's see what we can do. So we could pull out some factors and combine together the ln's and the e's. And then we can do one more thing, which is to use the log rule here, and so we've got ln of 24 over 17, I suppose. Not necessarily sure that all of this is useful or relevant, but it's nice to do, isn't it? Anyway, so that'll be our final answer. What about the second one? Well, the second one is a bracket. So we want to be thinking about what something to the power of 3 would integrate to. And we know that with integrating a power, you increase the power. So it's going to go to 4x plus 6 to the 4, divide by the new power, and then we apply our 1 over a. So our 1 over 4 would go with that. Limits for this are 3 and 2 again. So we're going to have, what's 1 over 16 overall, isn't it? Let's take that out as a factor. You can do this with definite integrals. You can always take constants outside if it makes your life easier. And then we want to do, again, I'm going to pause here. So if we sub in 3, we're going to get ourselves 18 to the 4. If we sub in 2, we're going to get ourselves 14 to the 4. And that actually works out as a nice answer. We're going to get ourselves 4,160 out of all that. Okay. And then for the very last one, remember we're going into radians here because this is a trig, even if this maybe looks to you like it isn't radians because there's no pi's, it is. We have to think, well, we got cos of 5x minus 3, so that would integrate up to sine of 5x minus 3, and we apply the 1 over a. So that's all we really need to do there. You can put in 0.6 and 0.5. I'm going to pause while I do that. Actually, no, I'm not. I'm going to show one more step. So we'd end up having to do a fifth of sine. If we sub in 0.6, we're going to get a fifth of sine 0 minus a fifth of sine of minus a half. So let's put that in the calculator. And we'll get that our final answer here is the really lovely fraction of 0.0959 to 3 significant figures. So yeah, not as nice as the differentiation chain rule, but still very powerful and still very useful. So what I'd like you to do is I'd like you to look at this big list of 12 functions, and I'd like you to tick and cross the ones that you think can be integrated or the ones you think can't be integrated, and maybe have an idea as to why. Obviously, some of them we will be able to integrate with rules we don't know yet, but with the rules we know at the moment, which of these can we actually integrate? Okay, on pause in 3, 2, 1. Okay, so first one, absolutely can integrate this. We know how to integrate e to the x, and our ax plus b is 6x, so our a is just equal to 6 in this case, and our b is equal to 0. Linear function is the key. Second one, no. Okay, well we do have an ax plus b, so that's okay, but there is no standard result for integrating ln yet. So that is not one we can integrate. We can differentiate it, we can't integrate it. What about the next one? Well, we've got ax plus b, that looks okay. But again, tan squared does not have a standard integral. Lots of things that are squared in trig do have a standard integral. We've got sec squared that we can get from differentiating tan, and we've got cosec squared from minus cot. But tan squared does not have a standard integral. What about the third one? X cos x. No, this is a deal breaker at the moment. We have no equivalent of, say, the product rule for differentiation that lets us integrate multiplied things. We will do. We're going to have integration by parts in a few weeks' time, but for now, that is a no. What about the fifth one? Yep, that's okay. Sine we can integrate, and we've got our ax plus b inside it. What about y? Well, we can integrate e to the x, but this is not ax plus b, so this is not something that we can integrate. What about the seventh one? Yep. we can integrate something to the power of 6, and we've got ax plus b inside. This is a no because of the x squared. This is a no because we don't have ax plus b inside. This one is a yes. We do know how to integrate cosec. It's going to go to cosec squared. It's going to go to minus cot, and here's our ax plus b. This one is a no because we've got a cubic inside our function, and we only can deal with linear things inside our brackets. And this last one is also a no because 7 to the x, that's not ax plus b. It's not something we can standardly integrate. So, I'd like you to pause one last time, and I'd like you to see what your results for those 4 integrals are. And I'll come back in 3, 2. Okay, so for our first one, we would go to e doesn't change, divide by 6. Second one, sine goes up to minus cos. And then we divide by 3, so I'm going to make that into minus a third. Third one, well, we know the power is going to go up to 7. We know we're going to divide by 7. And we also need to divide by the differential of the actual bracket of 4. And then the last one we could do, the cosec squared, did say that that went up to minus cot. So we know we're going to go to minus cot 9x, but we're also going to need to divide by 9. Hopefully you got those 4 right, but we've got some exercises to check it out now.